Alrighty, so between the last attempt, whatever that was worth, to now has been a few hours, many hours. I've considered this problem, and I did get a solution. I'll try to explain my thought process as best I can. So let's take an example. If I have a number that is 12,051, for every number in the sequence, starting with something simple like 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Each of those values has a certain number of following values or sub-values, you can think of it, where those sub-values would be skipped if you were to go on to the next number within that kind of level of number of digits, kind of. If you think of 1, 2, 3, 4, 5, 6, 7, 8, 9 as all having 1 digits and all kind of being on the ones digit level, each of those has a certain number of things that you would skip over if you go out into the next number. And if you have 1251 numbers, and let's say k is 300, or let's say k is something larger, let's say k is 800, you need to know how many numbers you would be skipping, how many sub-numbers that you would be skipping for going from 1 to 2 in order to determine whether or not you can make that jump. Assuming here that you have an algorithm that tries to do a one-pass loop or one-pass and determines whether or not it can go to the next value strictly based on and never go backwards. So it's gonna, so yeah. So if I were to think about 1251 values in the sequence and think about the sub-values or the values that are in the sequence after 1, it'd be 10 to 19. And kind of the sub-values between that would be 100 to 199. And sub that would be 1,000 to 1,999. Now, these sub-values are not necessarily strictly in order, I guess you can say, because when you go from 1 to 10, the next number then would be 100, the next number then would be 1,000 in the sequence, and the next number then would be like 1,001, 1,002, 1,003, 1,004, 1,005, 1,009, and then goes back to 101, and then goes to 110, 100, 11, or so 1,010, 1,011. So it's not necessarily that all these things are in order, but if you do skip over a particular value, then you would skip over everything sub that value, kind of. So the other thing that I thought about was, in general, the number of values that you skip over is a very consistent value. It's a very consistent kind of number. For instance, if you have 1 and you have some n value that is, in general, like let's say it's 4 digits, right? So let's say n is 3,000. The number of values that are between 1,000 and 1,999 is going to be exactly 1,000 values, and between 100 to 199, that's 100 values. 10, 19, that's 10 values, and 1 itself is 1 value. So if you were to skip 1 to 2, you'd be skipping over 1,000 plus 100 plus 10 plus 1, so you'd be skipping over 1,111 values. And similarly, if you skip over 2, you'd be skipping over another 1111 values because it'd be 2000 to 2000, 2000 to 200, 2000 to 2999, 200 to 299, which is like all these have the same number of values within their range. Now, a couple caveats is one, if within some block the value of n is found, or the value of n is in a subblock of it, then it's not the full complement of values that you're skipping over. So for instance, because n is like between 1000 and 1999 here, when you try to skip over this block, or this block only has 252 values within it, because that's the number of numbers that are between 1000 and 1251, like 252 numbers. So like if you skip over this kind of if you skip over these values, there's 252 values here, plus those values are part of the values that would be found within the 100 to 199 sequence, which is additional 100 values, so that's 352 values. And then if you try to skip this, this is part of the 10 to 19 values. Like these values can be found between like 10 and 19 in sequence. So that's additional 10 values. And then these all values can be found after the 1. So that's a total of 363 values. So skipping the 1 here is actually skipping 363 values exactly out of the 1251 values of this within the sequence. And skipping over the 2's later on would be skipping over like 1111 values. 100 values here, 10 values here. Like some of these numbers look kind of funky because I was using some other examples, but there'd be 10 values here, and there'd be 100 values here. Actually, so sorry, this would be 110, 100 values in here, 110 values here, 111 values in here. So what I ended up determining was, for any given value of n, I wanted to find, there's going to be certain values that differentiate the normal values that you can skip over. Okay, so let me try to be clear here. If you have a certain value of n, for each number of digits that you're working with, a number within that has that number of digits, if you skip that number and move on to the next number with the same number of digits, so like a two-digit number moving on to the next two-digit number, a one-digit number moving on to the next one-digit number, it's either going to have a value that is kind of unique because it's kind of it's part of the block that differentiates, like that has n within it basically, and because it has n within it, then it doesn't necessarily have the full complement of sub values that it would skip over. If it's not that, then it has the full sub values, which is like all the blocks below it combined to be the number of values that it skips, or it's like a factor of 10 less basically. So if you skip 1, it's actually, well, let's say the value is something slightly different. So let's say the value is it was like 2891. If you skip 1 within that sequence, then you'd skip over 1111 values. If you skip 2 within that sequence, it's not going to be exactly that much, because 2, the block that is between 2000 to 2099, that has 892 values within it. So when you skip 2, there's going to be like less than 1111. And then going on to skipping 3, when n is that, is actually going to only be skipping 1111 or 111 rather than 1111, because there's nothing that is within like the very deepest block that you're skipping over. So it ends up being that it ends up being something like this. I basically formulated a way of thinking or dividing the n into basically some number of tuples. The number of tuples kind of depends on the number of digits that n is, and for each tuple you have what I call a boundary value, and that boundary value is going to differentiate the spot where you have the full complement of values that you're skipping versus a partial value that you're skipping versus a smaller value that you're skipping. So here for 208 or 2891, if you skip over 1, then you have the full complement of 1111 values that you're skipping. If you skip over 2, like, let's say k is 1500, right? So skipping over 1, which is necessary in order for you to get to 1500, you're getting your kind of k value that you're looking at to be 1112. And then if you skip over 2, you're actually going to skip over like 1003, because 1111 plus 1003 is less than 1500 or more than 1500, then you can't skip over 2. But if you were to be able to skip over 2, then the things that follow 2, like 3, 4, 5, 6, if you skip over those values individually, then you're skipping over 1100 or 111 ones each time. And then breaking it down further, within 2 itself, each 2-digit number, or sorry, within the second level of this thing, if it's a 2-digit number, when you skip over any 2-digit number within the sequence, it's going to skip over 1100 or 111 values, except the special value that is 28, the boundary value that's 28. That value has 103 values that is kind of within it. After 28, there's each number that you skip there would be worth 11 values beneath that. And then diving one level further, if you have a 3-digit number and you go from like 3-digit number to 3-digit number, each 3-digit number that you're moving across is going to be worth 11 if it's smaller than 289, worth 3 if it's exactly 289, and worth 1 if it's after 289. And then yeah, and that's because like anything after 289, there's no 3-digit number that's smaller than that that has that kind of like there's no 2900 within n is 2891. So it ends up being that if you take your number to start with, you look at, in order to get these kind of tuples, and like for instance 1251, the tuples there would be 125 is worth 3, 12 is worth 63, and 1 is worth 363 in terms of how many values they're skipping. it ends up being that the tuple start with removing the last number, removing the last digit, the ones digit, and whatever that is, it's going to be the value of your remaining numbers is going to be 1 plus 1 plus 1 more than that last digit, so it's going to be 3. And those 3 exactly are within the sequence of numbers 125, 1250, 1251. Those exact 3. And here, this one's also 3. If you look at the 289, there's going to be 289, 2890, and 2891. So that's the first tuple. It's going to be worth that 1 plus like 1 more than the ones digit. And then for everything that is smaller than 125, 3-digit number that's smaller than 125, you skip over those. It's going to be worth 11 points or 11 numbers, and then if you after it's going to be just worth 1. And then going down one further, or going up one further, however you might think about it, the number digits would be just 2 digits here, and if you were to calculate how much things are worth, well, anything that's less than this is going to be worth 111 values. Anything that's after this is going to be worth 11 values. And then to get exactly how many values are beneath 12 or kind of hidden behind 12, it's going to be you take, because 12 goes in, 12 hides 120 to 125. Each of those, like 120 to 124, those set of numbers, 0 through 120 to 124, that's 5 numbers. 5 times 11, because each of those hides 11, is going to be like 55, plus an additional 3, because 125 has 3 itself, so that's 58. And then the remaining things after 125 through 129, because those are also within the 12, so it would be 126, 127, 128, 129. Those are worth 1 point each. So it's like 5 times 11 plus 3 plus 4, which ends up being 63. Is that right? 55 plus 3 is 8. 55, what was the formula? Yeah, 11 times 5 plus 3 plus 4 left over from 126, 127, 128, 129. Yeah, so it's 4 left over. And then if you go to the ones digit, think that 1 is going to be 1 itself is the value that's hidden behind it. 111 times 2, because you're dealing with the things that start with 10 and 11, they have 111 values there, plus the 63 from 12, plus an additional 7 values left over, 13 through 19, and each of those values has 11 within it. So anyways, it's a pretty complicated formula, and then it's a pretty complicated formula, and the code for that is, I'm not sure if this is all that great. Actually, I probably do need to do some cleanup here. Did I ever use numdig? Nope. So I start by doing the trivial case where if it's a small number of values and like less than 10, then you just return whatever k is. And then I call it cap here. Probably could just modified n, I think. I don't ever use n later on, but so basically n and I have an array of tuples. This is array of tuples to separate, to distinguish, to track how much each number with how much each number kind of hides or is worth in terms of the number of values that you skip in the sequence if you were to go to the next. You go to that number plus 1. And this is going to be, this can be tuples, is going to be the boundary value, boundary weight, I guess you can think of it, and then pre-weight, and then post-weight, where weight is number of values beneath it. So I skipped. So, did I ever use div? I don't think I used div. So I say the last thing is going to be the last digit plus 1. The current value of everything is going to be 1, and the previous value is going to be 0. And then while n, so this is just generating. So I'll just generating the special tuples. So while you have your cap is greater than 10, you want to get the front digits of it. So like the 1251, you want to get 125. And the current value of that 125 is going to be 1 plus whatever the previous value is. And this only matters when in the next iteration of the loop. So 1 plus 0, and then the value times the last. So it's only 1 times 1. 1 plus 1 plus the value of last year is 2 actually, sorry. So 1 plus 2. And this is actually going to be, this actually ends up, it's just being 0. So that ends up being 3. And so the front is 125, the current value is 3. Anything before this thing is going to be worth 11 points, and then everything after is going to be worth 1. And then next iteration of the loop, you want to divide out you want to remove the last digit from the current number, and you want to take the last digit of that number. So 125 becomes 12, and the last digit there is going to be 12. The value increases, so it goes from 1 to 11, and then the previous becomes the current. So the current is now 3. So the next iteration of the loop, you have the front is 12, the current is going to be 1 plus 3 times 11 plus 4, or sorry, 1 plus 5 times 11 plus 3 plus 4. Previous is 3, 11 times last digit is 5, yeah. So anyways, this is the thing. And then I reverse it up to make it a little easier on myself here. And then this portion is kind of slightly easy once you, this is the easiest part in the whole ordeal of this problem. Like once you have your tuples that differentiate the values that you're dealing with, the skip the skip values that you're dealing with, it's actually kind of easy to determine what the value should be. So you start with saying that the current value is 1, your spot in your kind of array is 1, the level that you're dealing with is 0. And while you still have more spots to go to in order to get to the kth spot, you say that you look at the tuple that you're dealing with for this level. So start with level 0, which is like your ones digit, your ones, and so you go 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So there's some boundary value that you have. So maybe it's like 2 or 3 that is going to differentiate like one that you're skipping that is like the full like 1111 versus the 111. So you take your current value. If your current value, assume that's your pre-value, and the current value is like the value that this is. Current value. Current value is number of values skipped for this value. Current value is number of values skipped going from current to current plus 1. So if your current is 1, current value is the number of values found between 1 and 2, including 1 itself. If your current value is 2, then current value is like how many values that you skip going from 2 to 3. Or if your current value is 111, then it's how many values that you would skip going from 111 to 112. Like, it could be 1,110, 1,111, so on and so forth. So if your current value is your boundary value, if your current is your boundary, then the current value is your boundary value. If your current is bigger than your boundary, then your current value is your post value. And then you check to see if you can move up that many, if you can skip. So check to skip current. So if you can, then you can skip over. So you go current plus 1, and the spot that you're dealing with is increased by the number of spots that are skipped, which is the current value. Otherwise, you can't do that whole jump. Then you need to go down a level. So your spot is still increased in your order by 1, but by going down a level, you will add basically a 0. So if it goes from 1 to 10, if this is going from 11, they just go to 110, so on, because that's always going to be the next number in the sequence. Your level increases, so you're dealing with a different tuple from the special array. And then if you're dealing with the level that's actually passed, then that means that everything else is worth 1. So you just increase your current by the difference between your spot k and break. So just as a kind of reference, this is what it looks like. I'll print out current current value, the level that you're dealing with, now the spot that you're dealing with, boundary, bound value, pre-value, post value. This is probably going to be too much. Okay, so this was a test case that that I had an error with. But so for instance here, actually let me print out so the special. All right, so the number here is 9 million, looks like. Yeah, 9 million something. So the special array of tuples is 9 is going to be worth 900,000 values beneath that. Anything that is 1 is going to be any number that is 1 digit that you want to skip over is going to be worth like a million. Alright, this is just too big. Okay. Let's look at this one. Okay. So here, this one's kind of stupid. Okay. Here, 1 is worth 363. If it's the smallest number smaller than 1, which technically there isn't any, it would be worth 1111. Anything after 1 that's 1 digit is going to be worth 111 values. And then on the level 2, anything that's smaller than 12, like 10, 9, or 9 isn't 2 digit, but 10, 11, those are going to be worth 111 values beneath it. 12 itself is worth 63 values, and then anything after 12 would be worth, that's 2 digits, so it's going to be worth 11. And similarly, at the 3-digit level, any 3-digit number that is smaller than 125 is going to be worth 11 values when you skip it. 125 is worth exactly 3, and then anything after 125 is worth 1. And so here, if we're looking for the 300th value in the sequence, or 300th entry in the sequence, that one's going to be, well, it's going to be less than, you can't skip 1 because 1 would be skipping over 363 values. So it's going to be beneath 1. So then you check 10. Well, 10 itself is going to be worth 111 if you skip it, so you should. So then you go to 11, and now you're at spot 2 plus 111, which is the 113th spot. If you can add another 111 to that and still be less than 300, so you go to 12, you're at the 224th spot. Here, the 12 is worth 63 rather than 111, and 63 plus 224 is still less than 300, so that's fine. So you're now at 13, and you're at spot 287. 13 is now worth, it's a 2-digit number that's after 12, so it's worth 11 points, or 11 values. So you can add 11 to that, and you get to 14 at the 298 spot. 14 is worth 11, but 11 plus 298 is bigger than 300, so therefore you're going to go down 1 level, so you're going down to 140. You're at spot 299. This is actually a 4-digit number, 4-digit number, or sorry, 3-digit number bigger than 125, so it's going to be worth 1. So you increment those until you get to 300. So you get to 141. Yeah. Alright, so I mean, this is my solution to it. I'm sure that there are much simpler ways of tackling this, but it's what I came up with. God, I hope I never have to do this problem again. Okay, and just for reference, this is, I think every solution that is normal is probably going to have the same speed, which is like 0 milliseconds or so, just because that's what happens when you have a fairly finite computation like this. Even if I had a bunch of code here, I don't think it would slow it down terribly. So anyways, this was speed. Huh. I swear it was faster in the previous iterations. Did I change something? No. It's probably almost certainly just random. I don't think yeah, it's almost certainly just random. Okay. Summary. I don't even know. Hard to summarize. Oh, let's try. So what I did was I made considered how many values are skipped going from any number to any number x to x plus 1, which is generally pretty consistent depending on the number of digits in x, and the size of n. So, for example, going from 1 to 2, where n is something that is like 4 digits, let's say, will skip over exactly 1,111 values. 1,111 values. With the main exception where the skipped values might include n, and those values can be determined directly by inspecting or by performing certain operations on n. And that was this whole setup here. I could take the last little bit, figure out how many values you're skipping from the last little bit, and then do the next level to it. So, so basically then created an array of tuples where each tuple stored info for the breakpoints, the breakpoints being the boundary values, where going x to x plus 1 generally will be either a full skip, so either like some value that is 10 times b plus 1 or v. So like it will either be that or the special value, or the special skip value, and then using those tuples move along the move spot along skipping over values, skipping from current to current plus 1 using the values associated with each skip. And this is fast because when you have that information, like you're skipping over pretty big chunks, like going from 1 to 2 if you're dealing with n is like a 9-digit number. Each skip there is going to be worth like roughly 1 million or so. So it's not trivial how much you're skipping. And you probably could even use a formula to determine how to make it faster than iterating through each one skip at a time. Like maybe you could formulate how you can skip more than one on a given level, or the level being the number of digits in the current value, in the current number. But you are doing it fairly quickly. It's order of magnitudes that you're skipping each time. Like at the very highest level, you're skipping something that is on the order of magnitude of the number itself, and then each level after that, you're skipping like a power of 10 less than that. But yeah, time complexity. This can be O of this O of n, I think, or O of k, where k equals number of digits in n that you're dealing with. Yeah, like the loop is basically going through k, but k skips over the spot here, skipping over current values, where current values is generally like powers of 10. Like current values like 1, 11, 1111, 1111, like yeah, they're powers of 10 basically. So yeah, as the while loop will move the spot to k, where spot increments by powers of 10. And then space complexity, this is going to be O of n for the tuples stored in the special array. And the number of tuples is basically the number of digits in n.